Hello and welcome to part 3 of lecture 10 of Math 1B03. So before we go any further, I just want to go back just briefly because I realized as I was writing this that I maybe forgot to include something, and I just want to point out here some things that you might want to double check in your textbook. So I used this particular fact twice in the last part, namely that all linear maps satisfy the property that all linear maps take 0 to 0. So if you have a linear map from V to W, it will always take the 0 vector from 0 to 0. And I use that fact in the first proof about showing that the null space is a subspace. But if you want to see a proof of that fact, you can see C311. And you can notice kind of the power of this result because I also used it again in the proof of showing that the null space is injective. So again, see Theorem 3.11 in the textbook. So we always know that a linear transformation takes 0 to the 0 vector. Okay, so I just wanted to highlight that before we talk about the next topic, which is the range. So given any linear transformation from V to W, the null space gives you a subspace of the vector space V, and then the range will give you a subspace of the space you're mapping to, which is the W. Okay, so let's kind of dive into the details here. So for any linear transformation, the range of T, and sometimes it's called the image of T, is the set of all things that look like TV as V runs through all the elements inside of V. And so this is a thing inside of W, because all you're doing is just taking each V in your vector space V and then plugging it into T and just taking the collection of all those things. And so let's look at those three linear transformations that I had at the beginning, of those three linear maps. And if I took T equals 0 is the 0 map, then the range of T is going to be, well, by definition, it's equal to TV, but it's the 0 map, so everything gets sent to 0, right? And this is true for each element V. So each element V gets sent to 0, so that means that the range contains of simply the single element 0, right? So that's the thing inside of W, where we treat 0 as the 0 vector. Okay, so there we go. There's one example. Let's look at our example of the shifting operation. Right, so remember we take an infinite sequence, we lop off the first term, and then we shift everything over to the right, and then we get a new infinite sequence. Well, the range of T in this case is going to be everything that looks like A2, A3, and so on off to infinity, where the AIs can go be any element in F. But if you stare at this for a second, what we get something that's kind of interesting is the range is everything. Okay, you can get any sequence that you want, because any sequence at F infinity, you can take that, you can throw any number you want at the beginning, so that would give you something that gets sent to this term into the second side into F infinity. Okay, so hopefully that makes sense that the range of T is F infinity. And let's look at our example that has kind of connections to linear algebra. So again, we have our linear map from F3 to F2. It's given by these formulas right here. And the range of T is we're just letting x1, x2, x3 range through F3, and we're just plugging them in. Now, you don't get much of a sense of what this set looks like, but notice that we can rewrite this as x1, and we get 1, 2 plus x2, and then we get the tuple 2, 4, and then we get the tuple x3 times the 2 tuple 3, 6, right? Where again, we're letting x1, x2, x3 run through F3. But if you stare at this for a second, you notice that this is actually a span, right? Or a linear spanning set of the vectors 1, 2, 2, 4, and 3, 6, right? So you can think of this as the spanning set of 1, 2, 2, 4, and 3, 6. Now, when we did this problem, we saw that there was a system of linear equations attached to this particular linear transformation. And in fact, we can connect it back to what's happening here, right? This is also called the column space of the matrix A, which look like 1, 2, 2, 4, and 3, 6, right? So this is from Math 1B03. So the range of T when there's a matrix kind of hiding in the background is the column space, right? So let me maybe make this clearer, right? So I have that if A defines the linear map T from Rn to Rm by Tx equals Ax, then the range of T is equal to what we call the column space of the matrix A. Okay, so this is the connection to Math 1B03. Now, as you might expect, like the kernel, the range is going to be a subspace. But now the range, right, by definition, lives inside of W, so it's going to be a subspace of W. And I'm not going to go through all the details. You could try to challenge yourself and try to do it yourself, or you could just look in the textbook. But basically, a result, all you need to do is check the 3 subspace criteria. Okay? But what I did want to talk about is what it means for a function to be surjective. So a function from V to W is surjective, and some books may use the term onto if the range of T is equal to W. Right? So it kind of explains why we would call it surjective, because we hit everything on the other side. Okay, everything gets mapped to on the W. Okay, so let me give you an example. So above example 2 is surjective, but examples 1 and 3 are not. Okay, and let me kind of justify why that is. Right, so it's clear example 1 is not surjective because we got 0, we didn't get the W, we didn't get the whole space. For example 2, the range of T was equal to where you were mapping to F infinity, so it's onto. Okay, so here, not onto, this is onto. And this one here, you have to kind of stare at for a second and ask, is this really onto? So you're asking is the span of this set, is it equal to F2, right? But you can convince yourself that this is the same thing as the span of 1, 2, right? Which is not equal to F2. It's because 2, 4 is a linear combination of 1, 2, and 3, 6 is a linear combination of 1, 2, so we can throw it away. Okay, so this is why it's not onto. So that's kind of all I wanted to say about the range and the the surjective property. What I want to do just to kind of get ready for the next part is start linking these ideas. So we have now a vector space, and we have linear transformations between vector space, and these linear transformations give us all sorts of subspaces. And the following theorem is kind of remarkable in the fact that it links a lot of these ideas. And it's called the fundamental theorem of linear maps. And it says that assuming that V is a finite dimensional vector space and T is a linear transformation or a linear map from V to W. Okay, so we're looking at V, some small condition on V, namely that it's finite dimensional. W, there's no condition on. And we're taking a linear map from V to W. Then the conclusion is the range of T is finite dimensional, but the more interesting thing is this relationship among the dimensions. Namely, the dimension of V is equal to the dimension of the null space plus the dimension of the range of T. So we get some connection between these subspaces. So we'll prove this in the next part, and I'll see you there in a minute.